Chapter 14, the second section of our notes. This comes from 14.3 in your textbook, titled Concentration and Rate. Today we're going to talk about what a rate law and what a rate law constant is. We're going to be able to determine the rate law for a reaction, and we're going to use that to find some other things involved with rates. So yesterday we learned that one of the four factors that affects the rate of a reaction is the concentration. And we had said that the greater the concentration of the reactants, the faster the reaction tends to go, because the molecules tend to hit each other quickly, more quickly, and more often. So one way we can do that is by determining the way in which the rate at the beginning of a reaction depends on the concentrations, or how the rate changes depending on how much of each reactant you have. For example, if we look at this reaction here, we've got ammonium ion, NH4 plus, reacting with NO2 minus, making nitrogen gas and water. In this reaction, we could look at a couple of different things. We could look at the concentration of ammonium or nitrite as a function of time, or we could look at how much nitrogen would be produced. Now let's look at how that changes over time. If we look at our data here, if we look at the initial concentration of ammonium, the initial concentration of nitrite, and then we look at the rate of nitrogen produced, notice a couple of things. One of them, notice that when the concentration of NH4 doubles, so looking at experiments 1 and 2, the concentration of ammonium doubles, the concentration of NO2 minus remains the same. When that happens, notice that the rate also doubles, goes from 5.4 to 10.8 times 10 to the negative 7th molar per second. Okay. Notice again in experiments 2 to 3, again the NH4 concentration is doubling, and again so does the rate again. And then if we look at one here, from 5 to 6, if we look here, NH4 remains the same, but NO2 doubles, and again notice that the rate is doubling. So there's definitely some trends there. One is that by changing the concentration of either of the reactants, in this case they always change. If one is held constant while the other one's doubled, the rate doubles. Now that is not always the case. Sometimes we'll see different data that shows that. What that shows is that, well, here, let's just get right to it. So what we do is rewrite what is called a rate law. This thing right here is called a rate law, and it is a law that is used to find the rate of the reaction. And the rate of the reaction is found by taking, notice a couple of things here. A is the concentration, notice the square brackets, of whatever the first reactant is. And then B is the second reactant with the square brackets. Okay, K is called the rate constant. And this little m and the little n we'll talk about here in just a second, but those are pretty easy to figure out. Now, what we find is that this little a here is the coefficient, and that little b is the coefficient. Notice that in no place in our overall equation down here do we have the little a or the little b. What that means to you is we do not use coefficients in balanced equations in rate laws. They simply are not involved with the rate law itself. So K is the Kate constant. It does change with temperature. The units for the rate constant can also change depending on these numbers up here. And we'll talk about that here in just a second. So let's say if we knew that that rate law happened for that last reaction was the rate is equal to the rate constant times the ammonium ion concentration times the nitrite ion concentration, we could calculate K. So if we just choose any of those experiments, and I think they use the first one, if we take the data from the first experiment, so that number, and that number, and we plug that into our equation, we plug it into this, here's our rate, The concentration of ammonium was that, the concentration of nitrite is that, and all we're solving for is K. Now, mathematically, please, please, please use your units. This is absolutely a section of the AP exam where they're going to focus on the units for your rate constant. Because when we divide molarity and molarity, we're going to end up with 5.4 times 10 to the negative 7th molar per second is what that means, over 0.0100 molar times 0.200 molar. Again, all you got to do is write it in there and see, hey, the molarities cancel. What's left? There's a molarity left on the bottom and a seconds left on the bottom. So the way you would write those units would be molarity to the -1, seconds to the -1. Let's say there was a molarity squared left on the bottom. Let's say this thing was squared. Then we would have molarity to the -2, seconds to the -1. So however many molarities are left on the bottom, that's the number that goes up here in the corner. So your answer comes out to be, in this case, 2.7 times 10 to the negative 4th molarity again to the -1, seconds to the -1. So once the rate law is known and K is known, then no matter what data they give us, we can figure out the rate. So now that we've calculated the value for K, if we change the concentrations, we can always find out the value for the rate constant. Now let's go back to those numbers up in the corner. So we had rate equals K times A to the power of M and what was it, B, I think, to the power of N. And these numbers are will always change, and you have to figure out what they are. The way that you figure out what they are is by looking at how things change when you change these concentrations. And again, we haven't talked about why, but because there is no number written up here for NH4 plus and NO2 minus, we say that those are both to the first power. If they're both to the first power, then you say that it is first order. So this reaction is first order with respect to NH4 plus, and it's also first order with respect to NO2 minus. The overall reaction order is a first order plus a first order makes it a second order reaction overall. So individually, it's first order with respect to NH4 plus and first order with respect to NO2 minus, but overall it is second order because first order plus first order equals second order. Okay, let's just see how do you determine those numbers up in the corner. They must be determined experimentally. You have to look at the data to determine what is it that number is being raised to. It can be raised to the 0 power. That means that if the rate, let's say our concentration of A goes from 0.50 to let's say 1.0, and then here you have your rate, and the rate goes from 2.5 times 10 to the negative 4th to 2.5 times 10 to the negative 4th. So the rate isn't changing at all. That means it's raised to the 0 power. Because this is going up by a factor of 2, this is going up by a factor of nothing, by 1. So 2 raised to what power equals 1? Well, 0. So it can be raised to the 0 order, the first order, the second order, but it can also be a fraction. It could be the square root. If something's raised to the 1/2 power, it would be the square root of something. Okay, so just like I said, if a reactant in the rate law has a 0 order, what effect does that have on the rate? It has no effect. So we just got to quit talking about this stuff and let's just see what. Okay, so here's a reaction. A is reacting with B to make C. They've done 3 different experiments. They want us to A, determine the rate law for the reaction. So we know right away that the rate law is going to be equal to the rate equals K times the concentration of A times the concentration of B. The only thing we're wondering about is what number goes right here and what number goes right here. So let's just look at our data. So I would say in comparing experiments 1 and 2, the concentration of A remains constant, but the concentration of B doubles. So B is going up by a factor of 2. The rate does not change at all. So it's not even changing. You're just multiplying it by 1. So then you just ask yourself, 2 to what power gives you 1? Well, anything to the 0 power is equal to 1. That means that B, with respect to B, this reaction is 0 order. And when you write your final rate law, you will not include B because B does not, as you can see, look at B. When B changes, what does the rate do? Nothing. That means B has no effect on the rate at all, so B will not be included in our rate law because it has no effect on the rate. Okay? So then let's look at A. What does A do? Well, you want to find an experiment where B doesn't change. So we're going to look at experiment number 1 and experiment number 3 because B remains constant. So we could say in comparing experiments 1 and 3, A doubles. It's going up by a factor of 2. What is the rate doing? The rate is going up by a factor of 4. So then you ask yourself, 2 raised to what power equals 4? 2 squared equals 4. That means that with respect to A, this reaction is second order. So when we write the rate law, our overall rate law is going to be the rate of the reaction is equal to the rate constant times the concentration of A squared. And that is our rate law for that reaction. On B, they ask us to determine the magnitude of the rate constant. Well, now that we know the rate law, we can choose any one of these experiments down here we want. We just have to put these numbers into the equation and solve for K. So if we use experiment 1, just because it's the first one, we can say that that A equals 0.1 and the rate equals 4 times 10 to the negative fifth. So we're going to have 4 times 10 to the negative fifth molar per second equal to K times 0.100 molar, and that whole thing is squared. Notice I put that squared outside of the parentheses. So then to solve for K, I'm going to take 4 times 10 to the negative fifth, and I'm going to be careful with my units here as well. So 4 times 10 to the negative fifth molar per second over 0.1 squared is going to equal 0.01. So that's 0.01, and I also have to square the molarity. So that's molarity squared on the bottom. So this molarity and one of these two molarities will be gone. So when I divide those numbers, 4 times 10 to the negative fifth divided by 0.01, I get a final answer of 0.004. And again, I've got my molarity on the bottom and I've got seconds on the bottom. So that's molarity minus 1, seconds to the minus 1. And I'm sure I probably got all this here. So this is kind of just showing it. So the rate is going to equal K times A squared. And I guess that's it. So now use the data. So the rate constant would be 0.004 molarity to the minus 1, seconds to the minus 1. Now they want to know, well, okay, what's the rate of the reaction if A equals 0.050 and B is 0.1? First of all, B we don't care about because, remember, it's not in our rate law. So the rate is going to equal K, which we just figured out was 0.004 molarity to the minus 1, seconds to the minus 1, times, so 0.004 molarity minus 1, seconds minus 1, times 0.050 molar, and again, A is squared. So you're going to have a molarity squared on top, you're going to have a molarity to the minus 1 on the bottom, so those are going to cancel. So you're going to have a molarity, one of the molarities left on top and seconds left on the bottom. So 0.004 times 0.05 squared equals, if we put it in scientific notation, 1 times 10 to the negative fifth would be the correct answer for C. Okay, let's look at one more. So we've got 3 experiments again. We've got NO reacting with H2 becoming N2 and H2O. So again, if we were to write this out without looking at our powers, we would have the rate is equal to K times the concentration of NO times the concentration of H2. Now let's look and see what nitrogen and hydrogen do to the rate. Now if we look at experiments 1 and 2, we can see that nitrogen monoxide remains the same, but H2 doubles. So that's going up by a factor of 2. 1.23 becomes 2.46. That's going up by a factor of 2. 2 raised to what power equals 2? The first power. That means that hydrogen, the order of the reaction with respect to hydrogen is first order. Now, I wrote the 1 just so you would see that, but if it is a 1, you do not need to write it. We know that it's a 1. Now, what does nitrogen monoxide do? Let's compare experiments 1 and 3. NO goes up by a factor of 2. The rate goes from 1.23 to 4.92. It's going up by a factor of 4. So 2 raised to what power equals 4? Obviously that is squared. So therefore, with respect to NO, this reaction is second order. So our rate law is rate equals K times the concentration of NO squared times the concentration of hydrogen. So now if we want to calculate the rate constant, again, it doesn't matter which one you choose. I'm going to choose the first one. So it's going to be 1.23 times 10 to the minus third. Oops. 1.23 times 10 to the minus third molar per second is going to equal, and then on the other side, K times the concentration of NO, which is 0.10 molar squared, times the concentration of hydrogen, 0.10 molar. So again, let's talk about our units. We're going to have a molarity squared times another molarity. On this side, we're going to have molarity cubed. Not molarity. We're going to have molarity cubed. And then when we divide it by the other side, we're going to have 1.23 times 10 to the minus third molarity per second, and we're going to have that molarity cubed on the bottom. So this molarity is going to cancel out one of these, so we're going to have molarity squared left on the bottom. And then number-wise, we're going to have 0.10 squared times another 0.10 is going to equal 0.001. So overall, we're going to have 1.23 times 10 to the minus third divided by 0.001 equals 1.23. And again, our units, we've got a molarity squared on the bottom, so that's molarity to the minus 2, seconds to the minus 1. Anything that's left on the bottom are always to the negative power. Okay, so that would be the rate constant right here. And then we can calculate the rate when we're given that data. So if we use this equation down here, the rate's going to equal K, 1.23 molarity to the minus 2, seconds to the minus 1, times NO squared. NO is 0.050 squared times, or excuse me, no, I did that wrong, didn't I? 0.5, NO is not squared. This is NO, this is H2. Hydrogen should be squared, so it'd be 0.150 molar, and that one is squared. So we're going to take 1.23 times 0.050 times 0.150 squared, and I get an answer somewhere right around 1.38 times 10 to the negative third. Now again, we're going to have molarity squared times another molarity is molarity cubed. Molarity to the minus 2 is going to cancel 2 of those 3 out, so you're going to have a molarity, and the seconds are still left on the bottom. So that would be your rate, molarity per second. Okay, so what we're trying to do today, we're trying to understand what a rate law is, how to get the rate constant. We've got to be able to determine a rate law once they give us that experimental data. If they don't have data, you can't determine the rate law. And then we were able to calculate the rate constant. This is a very, very important section, okay? And I'm not assigning this just to waste your time. This is very important that you be able to do that, especially these ones back here. Focus your efforts on those ones, and then certainly the ones from the packet as well. But these are the questions, what they're like on the real AP exam. And notice there's a lot of them, because guess what? This is on the AP exam almost every year. So make sure that you take the time, look this over, make sure you study it, and that you can figure out, based on that data that they're giving you, what the rate of the reaction is. Any of those ones you can't figure out, we will discuss tomorrow in class.